Welcome to the course of Fundamentals of Strength of Material. In this video I'm going to give you a brief explanation of the basic concepts and terms which we are going to go through during this course. This is going to be an introduction to the course. There are going to be lots of new things which I'm going to be explaining to you, and you will be overwhelmed at this point, but don't worry, the upcoming videos will explain these topics more thoroughly. So, strength of material is a combination of multiple topics which you have already learned during your studies. We will be combining mechanics, material technology, cross-section parameters, and some empirical information and standards to fully understand the strength of materials. During this course, we'll be focusing on basic cases. We're going to be talking about really basic calculations and some basic functions. And if you wish to study more on this topic after this course, there are following courses which you can take. So, as a summary, the ability, if you wish to be able to calculate the strength of materials, you must have understanding of different concepts and terms which we're going to go through, and you must have the understanding, especially in the mechanics. If you haven't studied mechanics yet, I highly advise you to study mechanics prior to taking this course. So first, most basic scenario is the axial or normal stress. On this slide you can see there's a simple case where there's a round bar and there's a force of 15 kilonewtons that is pulling on the bar. Okay? Since we all know that there's a force and there's always a reaction, so you can see that the same force is applied to the both ends because there has to be reaction force as well. So this object is stationary. It's in equilibrium, as you know from mechanics course. So what is stress? Well, the stress is the internal load inside the particle or inside the component which we are talking about. In this case, the round bar is subjected to external load of 15 kilonewton on both ends, and inside the material the iron atoms are trying to hold on to each other. They are experiencing stress. So the force is trying to elongate the part, and the iron atoms are holding on to each other, trying to withstand under the stress. The basic formula how we calculate stress is normal force divided by the area of cross section. A normal force in newtons in here, and area of cross section in square millimeters. It's really important to know or understand and remember during this course that every time when you do any calculations in this course, you must always make sure that the units of stress is in newtons and the unit of cross section is in square millimeters. When you use the correct units in there, you will get the unit which comes out from the calculation will be in megapascals. In SI units, the unit of stress would be in pascals, but since the stresses that we are going to be talking about are so high that the pascals would result in really long numbers, hence we prefer using megapascals. That is the standard in industry as well. Here's a simple example. So like I mentioned, there's a round bar, cross-section area 70 square millimeters, okay, and the force 15 kilonewtons, so 15 kilonewtons is 15,000 newtons, and the 15,000 newtons is divided by 70 square millimeters, and the resulting stress in this case is 214 megapascals. Okay, pretty simple. Is 214 megapascals a lot or not? Well, if you think that if that material was steel, basic structural steel, S355 for example, the yield strength for S355 would be 355 megapascals. So if that round axle was made out of basic structural steel, it would withstand that load. Okay, so that is the first one. So important thing, the formula normal force divided by cross-section area. Units will be megapascals. The letter denoting stress is Greek letter sigma. Okay. Number 1. Number 2, shear stress. Well, the basic formula for shear stress is pretty much quite similar, but instead of having normal force, we have now shear force divided by the area of cross section. And the difference in here is that the shear stress is denoted by letter tau, Greek letter tau. Unit exactly the same. Just like in normal stress, in here we also want to have always the force in newtons, cross-section area in square millimeters, and the resulting unit will be megapascals. Here's a simple example. There are 3 plates. They are joined together. They are held together by this pink bolt in here. There is a force that is applied from down here. It's pulling towards ground, and these 2 plates up here, these are mounted to something. So they will stick in place, and there's a force that is trying to pull the plate down. The bolt in between is the one that has to carry all the load here. So the bolt is actually experiencing so-called shear force or shear load. Okay? So here's the same thing. So this plate has been separated from here to visualize a little bit better what's happening there. So you can see that the bolt is, both sides of the bolt are experiencing or are trying to support the load here. So you can see, you can remember from mechanics that when we have a equilibrium state, we can make a free body diagram. This is basically now the free body diagram of this case. The sum of vertical forces has to be 0 when we are in equilibrium state, and hence one side of the bolt has shear force of 7.5 kilonewtons. So in here, this one side has shear force of 7.5 kilonewtons, right? So when we want to calculate what kind of stress this one side of the bolt is experiencing, tau, what kind of stress it's experiencing, how we calculate it, we take the 7.5 kilonewtons, we convert it to newtons, so 7,500 newtons, divided by the surface area of this one side. The surface area of this one side is calculated just like you all know, pi times the radius powered to 2. And the resulting stress is 95 megapascals. So that's how we calculate basic shear stress. Well, if this material was steel S355, because this is shear stress, we cannot use the yield strength directly. A good estimation for a shear strength of material is to multiply the shear and the yield strength, the tensile yield strength, with 0.6. Alright? Okay, so that was the second concept in this course. Let's take a look at the third one. So, third one is bending stress. Just like the bending stress is basically a special case of normal stress. So, in normal stress, we were just pulling or squeezing a piece of material. But in bending stress, like the name suggests, we are bending things. Okay? So here I have a basic plastic card which I'm bending, and you can understand that when I bend this material, it's experiencing some sort of stress. Here on this slide is a basic example. There's a rectangular cross section which is bent. We're bending the cross section, and when we bend cross section, when we bend material, what actually happens is that the other side, in this case the top side, is experiencing compressive loads, and the bottom side is experiencing tensile loads. Okay? How do we calculate the stress in this kind of cases? Well, there is a simple formula. Once again, it is looking pretty much the same, just like before, but in this case, we need a new term. we need to know the bending section modulus, and also we need to know the bending moment. The bending moment is equivalent to the force in this case. The bending moment is the force that is actually causing the stress, and the bending section modulus describes the stiffness of this cross section. Don't worry, I will be teaching you how to calculate the bending section modulus, and the bending moment you should already know from the mechanics how to calculate that one. So, one thing to notice here is that once again, the symbol for bending stress is once again sigma, so just like it's for normal stress. The reason is that this is basically a special case of normal stress, and the material is tensioned or compressed just like in normal stress cases. And once again, really important thing, the unit, it will be megapascals. The bending moment, as we know, is typically Newton meters, but like I mentioned, you must always make sure to convert your units to millimeters. So in this case, the bending moment will be in Newton millimeters, and the bending section modulus has a unit of millimeter power to 3. You will learn that when we do the calculations. Okay, 3 done. Finally, the fourth one, shear stress in twisting. We're gonna be studying also this topic. This is a case where we have, for example, in this example, we have a round bar which we are applying torque into. Okay, so we're twisting the round bar, and this is causing shear stress into the cross sections of the material. Once again, because it's a shear stress case, you can see that the letter which we're denoting this is tau, just like it was in the basic shear case. And how we calculate it, the value for shear stress is pretty much once again similar than the 3 cases before. We have torsional moment, we have torsional section modulus. I will be teaching you how to calculate the torsional section modulus, so don't worry about that. Once again, newtons and millimeters are the units, and the result will be in megapascals. So now I have introduced you the 4 basic cases which we're going to be studying during this course. The next really important thing is to understand when we apply load to material, when we pull it or we push it, when we apply tensile or compressive loads, what happens is that the length or the size of the material will change. And the change in the length is called strain. Okay, the strain is the relative change in the length of the material, so it's kind of like how many percentage the material's length has changed. Here we have 2 different ways how to calculate the strain. During this course, we'll be focusing mainly on this first one, and now I will explain to you how it works. So the strain is the relative change in the length of the material. So here we have a simple example. We have a bar that has length of L. Let's say the length is 2000 millimeters. And when we apply force to the bar, it will get longer. It will get longer, let's say 3 millimeters. So the final length of the bar is the original length plus the 3 millimeters. So it will be 2003 millimeters long. Well, in the first case, how we calculate the strain is the Lagrange strain, the one which we will use in this course mainly. The strain is calculated the change of the length, so 3 millimeters, divided by the original length, so it will be the 2000 millimeters. And here we have the example, 3 millimeters divided by 2000 millimeters. The strain will be 0.0015. Right? Quite simple. Well, because as you can see, the strain values which we will be talking about, especially when we're talking about steel materials or metals in general, the values will be really low, and hence quite often we use microstrain to get rid of the comma and instead have like a number that is a little bigger. So in here, for example, the micro is 10 power minus 6. So you can see that the 0015 will be 1500 microstrains. The Euler strain, the other way to calculate these things, is mainly used for soft material, materials like rubbers, for example, which have which are really soft. So when you apply load, they can get really quite a lot longer. The difference between Lagrange strain and Euler strain is basically that in Euler strain, the change of length is divided by the final length of the material. So in this example, it would be, now the change of the length would be still 3 millimeters, but the final length, the total length after the elongation is 2003, so the divider would be 2003. And you can imagine that if we would calculate 3 millimeters divided by 2003 millimeters, the difference in the strain value would be really small. So in case of steel materials, it is the result would be pretty much the same. So, final and really important thing that ties these two things together. So when we're talking about stress, we also, and strain, there is a relationship between stress and strain, and the relationship is called Hooke's law. You might remember from material technology course, when you did a tensile test for material, you might remember a curve something like this. In this curve, the linear section before the material yields is a linear relationship between the stress and the strain. And that relationship, the coefficient factor or the slope that describes this relationship is called Young's modulus, or modulus of elasticity. That is a really important material property, and it's a constant material property. When, for example, for steel, the material property, the constant will be 210 gigapascals. What does the Young's modulus describe? Well, the Young's modulus describes basically the stiffness of the material. So the higher the Young's modulus, the stiffer the material is. In case of steel, like I mentioned, the Young's modulus is 210 gigapascals, and for example, for aluminium, the Young's modulus is 70 gigapascals. So you can understand that the steel has Young's modulus 3 times that of aluminium, which means that steel is 3 times stiffer than aluminium. The formula that describes the relationship between the stress and the strain is like this. So if we know the elongation of material and we know the Young's modulus of the material, we can calculate the stress. Or, in quite commonly, if we want to know the elongation, we want to know the strain, we want to know how much longer the material got, and we have already calculated the stress, we can calculate that by using this Hooke's law. Well, that's it. Those are the main topics which we are gonna go through. There was a little more material, a little more content in these slides. You can take a look at those, but those were the main and most important things from these slides. I highly recommend that you take a look at these slides, take a second look at these slides, and hopefully you will understand them. Okay, I'll see you on the next video. Bye.